Hello, I'm Christopher Forbes. My presentation is about the analysis of a paper about the modeling of the dynamics of language death. This paper attempts to create a model detailing the relationship between two or more languages in regions of the world which contain two languages, one differing from the national. Such regions of the world are things such as Scotland, Wales, Spain, for European examples. There's also Peru. In these examples, the native language has now been replaced by the national language, and national language is being taught, so they cannot learn that language anymore. Example, with Catalonia, it has the language Catalan, and it's slowly dying out, unfortunately. This paper models the dynamics of this relationship so it can better be explored and prevented as seen in certain countries like the province of Quebec in France. To acquire the data for this model, historical data was used and fitted to the model. The paper makes several assumptions. Each population of speakers of a language is highly connected with no spatial or social structure, and it's monolingual, meaning that there is no segregation of a language. Speakers can swap between only those two languages, and the fractional portion of one language is complementary to the other. A language without speakers or quote-unquote status, as the paper puts it, will not be adopted, and the probability that someone will swap is smooth. The probability function that dictates this is continuous and not continuous. The equations modeling the system are seen here. The change of x over the change in time is equal to the fractional portion of speakers of language y times the probability that a y speaker will change into an x speaker, and the fractional portion of speakers of language x times the probability that a x speaker will change to y. We can represent y as 1 minus x. We can represent the probability functions in the same manner, and we can represent the probability function as the constant c times x to the power of constant a times the status of the language. Thus, we can plug those in, we can get the whole representation. Here are the results that the paper found with graphs taken from the paper. A representing Scottish Gaelic in Sutherland, Scotland, B representing Quechua in Huanco, Peru, C representing Welsh in Monmouthshire, Wales, and D representing Welsh in all of Wales. There is a recent status change as found in the paper, and this is represented thusly on the graph. This is the results from my Simulink analysis. The values for C for all examples were unfortunately not provided by the author of the paper. However, the value of A was being 1.31 plus or minus 0.25. We can see here when the value of -1 was used for C, we got something that approximates the shape of the graph. However, the x-axis is incorrect for the amount of years provided. Here we can see the difference between the two. Further analysis has, by plugging in random numbers into C, has shown that C is somewhere between -1 and -0.001 for all graphs. A value of -0.01 yields the graph to the right. C is probably for all cases between -0.2 and -0.05 is what I would say upon even further analysis. Raising the cultural constant to 5 causes language to be very quickly eradicated. This is 15 standard deviations from the mean, however, and is unlikely to occur in any language. The conclusions that we've seen from the paper are that each language experiences a sudden drop of popularity upon initial mixing, and then after hitting a midpoint, slowly declines into no speakers. However, the equation does not take into account efforts by the government to prevent language decline, as seen in the example with Wales, wherein there was some efforts by the government to stop it from declining entirely, and there is a change in status of the language as seen on the graph. This is the diagram that I've created. It is a mess along with every other one of my diagrams, but it works very well. This is my citation. Thank you all for listening.